Hello and welcome to the session on the return on invest of static code analysis and software architecture verification. My name is Sebastian, and I was one of the co-founders of Axivion, which was acquired by Qt in August this year. And now I'm business acceleration manager to make sure that the success that we had at Axivion will not only continue, but will be leveraged and brought to a next level together with Qt. As I said, we are part of the Qt group since August and part of the quality assurance business. And I will talk about how quality assurance with the specific aspect of static code analysis and architecture verification can make you more successful and especially more successful in a way of return on invest to develop software faster, better, cheaper, and with happier developers. So before I come into that, I will give you just a rough overview about some of our customers that already profit from Axivion Suite, just to show you that no matter where you're from, if you're developing software for cars, planes, and other industries, medical, it really does not matter. What unites all of our customers is that they are caring about quality and that they either because of their intrinsic motivation that they just want to have the best quality possible to deliver to their customers to be successful and competitive, or with an extrinsic motivation that there are some regulations and rules that force them to do certain things to ensure their quality, and a combination of both, obviously. So that's just a rough overview, maybe a rough overview how we support you with being successful with using our tools is not only with the tools themselves. It's, of course, that's what I'm going to talk about now. It's the tools in the end that will make all this return on invest possible because you need to automate these things in order to make it part of your daily business and to make it efficient enough to really get a high return on invest. But as you probably have all introduced new tools in the past, you know that it's not like install next, ready, and then everything is up and running. And in order to make it as smooth as possible, we have a professional services team that supports all of our customers from day one to make it seem as if it was just next, ready. So we will not only offer you the best tools available to do static code analysis and architecture verification, but also offer you the services around it to set everything up, integrate it into the existing processes, integrating it into the existing technology that you're already using to make it a quick success so that you can have that return on invest as quickly as possible. So this was it for a quick introduction. And now I'm starting to get to the point on where you can really gain benefits from our analyses. Let me first look at the root cause of why software development is sometimes more expensive than it should be, is sometimes more buggy than it should be, less plannable than it should be, more stressful than it could be. And the root cause for most of these issues that we all see in software developing is that when you develop software over a long time span, and long, I mean a couple of years, so not only having one version and then go to the next greenfield project, but really having a lot of brownfield projects where you continuously add new features to existing software, where you try to combine things, where you try to get product lines. When you do that, then there's empirical research way back to the 70s that the internal complexity of the software projects that you have is increasing disproportionately over time, almost exponentially. And that happens with pretty much every project, independent of what processes you use, what languages you use. It's just something that happens if you don't take precise measures to counter steer. So, spoiler, there are measures, there are things you can do. So that's why I'm having this session. But to realize why it's so important to do it is not only because of the return on invest that you gain to be quicker on the market with all these things, and having less bugs is cheaper, obviously, too. But because also when you reach a certain level of complexity in software projects, then you reach a sort of boundary where your software developers can still comprehend, understand, and overview the system. And when you reach that point, it will get very hard and in a later stage impossible to make changes in your software to add new features. And that's something you definitely don't want to happen before you say, okay, this project is finished for good anyhow. It's end of lifetime for the product. So we have a new greenfield project. I don't care about the complexity and the maintainability of my software. But it often happens that you reach that boundary of comprehensibility and maintainability that before end of lifetime of your product. And then with life gets really hard. And what you can do about it is to look at what parts of the complexity of your project are really complexity in a sense. When the project has more functionality, it gets more complex by definition, and there's nothing much you could do about it. And where's really complicity? So that you say it is unnecessarily complex. And that's actually the trick here, to make it possible that you stay on a path where your software project stays maintainable until the point where you say it doesn't need to be maintained anyhow. And in order to do that, you have to focus on the things that are avoidable. You have to find out what complexity is unnecessary and make it part of your day-to-day business to ensure that this unnecessary complexity does not sneak into your projects. And that's exactly what we do using our tools. So we continuously detect unnecessary complexity so that your development team has a chance to directly counter steer before you reach a level of complexity where you're really in trouble. So that's actually what we're doing. And we're using static code analysis and architecture verification because you can really cover most of the things that can be tackled when we talk about unnecessary complexity. And these are basically these issues here. As I said, architecture violations and hidden dependencies, that's something you can use architecture verification for to make them disappear. As part of our static code analysis, we have a clone detection and clone management system. I'll come to that in a second, what that means. We make sure that your functions do not get too complex and get out of hand. We check for violation against coding rules. Might they be in-house or standard coding rules such as MISRA, AutoSAR, C++14, and so forth. We make sure that there's no dead code, and we check for anything in your software that is a cyclic dependency on a function level, on an include level, no matter what, because anything that is a cyclic dependency makes your life unnecessarily hard. That's why Microsoft introduced that circle dependency warner in Excel many, many years ago. All right, so let me just go quickly over these 6 issues to just quickly explain what they are, and then I will show you what's the return on invest of actually tackling these things and making sure that your system doesn't end up like depicted here. You should have a software architecture documentation anyhow. And let's be honest, we all have software architecture documentation somewhere. And if it's just in the heads and in the memories of the developers, it's there. Somebody knows how the system is structured. Or if you look at your folder structure, or if you have some Word documents, or if you go all the way having fancy UML diagrams using tools like Enterprise Architect, Rhapsody, or so and so forth. The thing is that if you have these architectures as depicted here in the modeler that we ship together with Axivion Suite, for anyone that is not using any modeling tools so far, we have a no-frills approach to say, okay, this can do anything you need to really model and document your software architectures, and that's it. So it's a very easy way to really document your software architectures with a couple of clicks. So you just decide you have certain components and dependencies. Super simple. The thing is, with any software architecture, if it's Word or Enterprise Architect or whatever, you're not always, or actually never really sure if what you have in the code is really exactly the same thing that you have in your architecture description. And this is dangerous because of two reasons. First of all, this violation against the documentation could mean that there's really something wrong. So things are happening that should not happen. And the second thing is that if they're not documented, you have hidden dependencies where somebody can really get a problem, because if you, for example, trust your architecture that you have a nice and clean hardware abstraction layering and you don't, then you change something. And we all know that obsolescence is a real issue right now. And then you change something, trusting your hardware abstraction layer, and weird things happen. And to find out why they happen, where they happen, and fix these bugs can be a real nightmare, and it can be really costly. And that's why the architecture verification of Axivion is such a game changer for you, because we have the possibility to import a software architecture from our own modeler or from a UML tool or even from an Excel file and map that architecture onto the real dependencies of your code. And we have the luxury to have an absolute state-of-the-art static code analysis under the hood. So we really know about all the dependencies, not just calls, but really everything from usage of global variables and so forth. So there's really nothing, or pretty much nothing, that we cannot detect, because there's data and control flow analysis under the hood as well. So, and we can then tell you, as I'll show you in this example, that there are certain parts here where there are dependencies which are marked red here and here that have actually not been documented. And getting this information on a continuous day-to-day basis brings you into the position to make a decision if that is just a hidden dependency, which then means just simply document it and that's it, or if it's a violation against your architecture concept, so you must think a bit more to find another way to implement this feature. But this transparency automatically gets rid of all hidden dependencies, and at no cost, by the way, because just the transparency already saves you a lot, and you don't have to change a single bit in your code or in your architecture documentation. You just know it, and by knowing it, you don't have any more hidden dependencies. And of course, it gives you the possibility now to really keep your software architecture clean in the long run, because you can avoid these architecture violations, which just happen because there's a lot of misunderstandings. Typically, if you have software architects and developers talking to each other, they think they understand the description exactly the same, but in the end, it comes out that they don't. This is not only an important tool for architects, like looking at it in this modeler, but it's an important thing like for each and every developer to get this information. And that's why we have those IDE plugins, for example, and other means that the information directly pops up in the developer's workspace. So in my example, when I said there's a violation against the hardware abstraction principle here, somebody's Xing stuff that they shouldn't, they just should have used the interface, then he or she would directly get that measure and can counter steer. And the same thing with transparency, getting aware of the issues and the unnecessary complexity that will make your life hard and difficult in midterm and long term and expensive, is also that we have a clone detection and clone management system. What that does is it finds identical or almost identical parts in your code. And I'm not talking about structural identical code parts, but really it is the same code in the sense of a syntactic analysis here. So as you can see, these parts here, they're almost the same. The only thing is that the identifiers have a different name. You can see that here it's SAJ1 right, and here it's MD5 right. and so forth. The rest is identical. So therefore, we know it's a type 2 clone, so it's structurally identical, but has renamed identifiers. And how that helps you in terms of return on invest, I'll come to that in a second, but this is just for you to get familiar with what clone management actually does. It manages your clones all the way through the life cycle, because it's not about avoiding all the clones. Sometimes copy paste is a really good and fast and risk-free way to reuse code. So it's not that we say, oh, you should never do copy paste programming. But if you do so, you must absolutely keep track of your clones to make sure if you make changes, that no errors happen because these changes are inconsistent. The next thing is that we check, as I said, is anything that's cyclic in your code. So if you have include cycles, as in this example, we would find that out. And as you can see that you absolutely need tools for that, because if you have 4 entities like here, or it could be even more, then it's impossible for you to find these things in a manual review. Like you could see it if within one function you have a function cycle, okay, and you can make sure that there's no recursion. But with larger ones, larger cycles, you stand no chance in manual reviews. And talking about function cycles, obviously, they can produce errors that are obviously not nice because you can run through recursion. Next thing, as I said, is dead code. So any dead code that can be dangerous because of 2 reasons. Again, maybe the code is unintentionally dead, so it should be called, but you don't. Or it's dead and nobody uses it, but people still read it, write test cases for it, and so forth. So it's just useless. So get rid of it too. Next thing is, if there's functions that are getting too long, too nested, untestable, and so forth, it's important that you become aware of that. Again, it's about transparency, bringing you into the position to do something about it. And last but not least, as I said, coding rule checks. That could be naming conventions, for example, if you have them. But it, in this case, can also be like something like an AutoSAR C++ rule that we check, or a CWE whatsoever. Again, it's important that it's on a continuous basis, so the developer also has some learning experience. When you get direct feedback, of course, it will improve the awareness also of your developers for these coding rules. To make that all happen, it's not only important that the developers get it right away, but also important that they get it in an automated way. That's why everything that we do, we recommend to do it as part of your continuous integration, continuous build environment. So it's guaranteed that these checks are continuously done and nothing can slip through. And if you manage to do that on a continuous basis, you can really save a lot of time and money and nerves and mitigate risk, because you now stay ahead of the game. If you really know what you're doing, if you have full transparency about your architecture, if you manage your clones, if you make sure your functions do not get unmaintainable, if you stick to the coding rules right from the start, if you make sure you don't have any dead code and no cycles, or if you have to have cycles, you exactly know where they are, then you're good. And more in detail, I come to these return on invest aspects now, is that if you use static code analysis and architecture verification, this risk mitigation happens on many levels. For example, when it comes to defects, of course, when you exactly know where you are in your architecture and you can trust your architecture, the risk of having defects because of interfaces not used, for example, or global variables being used that nobody is aware of, that of course can avoid mistakes. Also, it will mitigate the risk of not meeting deadlines. So the project planning gets more mature and more reliable too. So overall, this protection from unnecessary complexity, what we call software erosion, it really reduces your risks dramatically. It also brings you in the position that for this long period in time, you will stay in the position that you can always quickly react and flexibly react to any new requirements. Might it be customer requirements or market requirements? If you have a system that is not maintainable anymore, where you cross that boundary of maintainability and comprehensibility, then you might be in the position to say, you know what, it would be a great feature, but actually, no, it's going to be too risky and too expensive. Instead of keeping a system nice and clean in the long run, you will always be in the position to make changes without any big risks or without any costly effects. Also, from that overall perspective, of course, securing the investment of years of development work is an important issue. If you spend millions and millions of euros or dollars developing large software systems, it's just a shame to throw all that away, to throw it in the bin and have to start from scratch. And so that's definitely something we want to avoid, because then we're no longer really talking about return on invest. It's any investor would have been worth it to avoid that. Now we get more into detail. These aspects are true for static code analysis as well as for architecture verification. There's specific things where you can really look at return on invest on the level of static code analysis. Let's take an example from the automated coding rule checks, like this one, which is part of MISRA. It's an example where you should have braces when you use macros. Why is that? You can see that example. If I replace x by 5, like if we calculate 5 times 5, it's quickly done. It's 25. But if I ask you now, so if you replace x by 2 plus 3, and hint, those braces are not going over there, it really takes some time to make the calculation. I'll let you think a bit. Let's see what answers you come up with. The right answer is 11. It's logic, like if you take 2 plus 3 times 2, so it's 6 plus 2 plus 3 is 11. But already here you can see, of course, it's solvable, but it takes you more time, it puts you under stress, and yes, you can make an error. So that can just happen. And that's such an easy way to reduce these risks by having those coding rules. If you have these braces here, nothing happens, you're safe. So this is just one example where you can really reduce risk by using static code analysis. You can reduce not only risk, but really get an efficiency increase and a reduction of your defect costs by using a clone management system. Because if you don't have such a system in place, then if you get a bug report and you find the bug, remove the bug, and test the bug in a way that, did I really remove the bug? And maybe I introduced a new bug by fixing it. That's a lot of work. And now it can happen if somebody did some copy-paste program that a similar or actually the identical bug can pop up in another place sometime later and in another place. And nobody guarantees you that your test will find all of these things. It could be 3 different customers reporting that. And that's really nasty. So because if there are clones, your bug is cloned as well. And the efficiency increase can be really easily calculated, because if you have a clone management system, then as soon as you have a bug report somewhere and you localize that bug, then you directly know, using our clone management system, where to remove the bug. So you just have to do it once, test it once, and are safe now. And if you calculate how much that brings you, it's pretty easy. Like we know that on average, like around 10% of the code is cloned. So maybe it's 8% or 12% with your project, but like roughly it's around 10%. If we make the assumption that we have an equal distribution of errors, then 10% of your errors will be within clones. And if we look at the empirical data, then, and we know, first, another assumption that we assume that we only have clone pairs, so no triplets and so forth. So it's an underestimation. If you have triplets, is of course even more savings that you have. But here, even if it's just pairs, we know that every second of these errors could have been saved with a clone management system, so 5%. And if we now look at the empirical data that around 20% of the total development costs are error costs, then we can just simply calculate that you can roughly save 1% of your total development costs every year just by using a clone management system. And that doesn't cost you anything. What can also, where the clone management system can also be used is if you find clones that can be replaced or refactored, in the special case when it's really an issue with saving memory footprint, reducing memory footprint. And there, of course, not only the clone management system can help, but really also the dead code detection. And nice side effect, not only can you save memory, you really speed up the program understanding of your developers. So that was like some examples for static code analysis and what the return on invest is there. Now let me come to architecture verification, where the return on invest is even higher. If you look at the cost for software development, you have design, analysis, design, implementation, and test. Then if you have projects that take a couple of years, then this only becomes a small amount of your total development cost in a project. So up to 20%. In long projects, meaning long development cycles, like the project is existing for many years, it can be even less than 10%. The interesting thing is, no matter how much that initial development cost is and the total development cost for making maintenance and adding new features, the interesting thing is that in that phase where adding new features and maintenance come into play, only half of the time is typically spent with productive work, whereas all the time was productive in the initial development, the greenfield project. In a brownfield project, it's only roughly 50%. And the other 50%, your developers typically spend understanding existing software. And there's empirical research that a quarter of this time, so speaking in total development costs, roughly 10% of the time, they spend time finding out that there are dependencies in the code that they haven't been aware of. So by just getting rid of those hidden dependencies, you can roughly save 10% of your total development costs. And even if you say we have such a stable team and we all know what we're doing and we have great architecture documentation, make it 5% or make it 2 or 3%. It's really, really a big chunk, a big possibility to really save a lot of time and money. Also, it's clear that the earlier you find errors, the better it is. That's why you do testing. You don't wait for your customer to find out if there's a bug. And that's why you do static code analysis, because that's something you can do even before testing. That's the great thing about static analysis, because you don't have to have test cases. You don't have to have a system that's really running. You just have to have some code that compiles. And architecture analysis saves you even earlier. So it's the cheapest point in time when during an analysis and design phase of a new feature, you can find out that there might be a problem. So you can really have a lot of possible savings there as well. And that's something to consider. And also some return on invest that you have that's hard to calculate is how dependent are you on single developers or architects that really get an overview about the whole system. So you could always go there and ask them, how's that structured? How does that work? So great people. We all have them in our teams. But what happens if they're like just absent or absent even in the long term? There's fluctuation. They leave the company. It leaves a lot of people with a lot of question marks above their head because nobody really knows how the system is structured anymore. And this risk can easily be mitigated by just having automated architecture verification because you are aware of all the real dependencies, not the documented dependencies, but the real stuff. So even if, as in this picture, there's still stuff red or yellow, which actually means, okay, you thought there is something, but there isn't, then you are not in trouble. Summing it all up, the return on invest of static code analysis and architecture verification happens on a lot of levels. Bottom line is actually staying ahead of the game, staying in control, not letting the software and the complexity control what you're doing and when you're finished, but really being able to plan and having less errors and so forth. But of course, it also it's about preserving the ability to react quickly and flexibly to customer market requirements. It's making sure you reach your targets in the meaning of on-time delivery, being ready when you planned you're ready, protecting your R&D investments, not to be in the position to have to throw everything away, increase the productivity, reduce memory footprint, reduce overall defect risks, and mitigate risk of employee absence and fluctuation. And speaking of fluctuation, one thing that our customers tell us, using all these tools increase employee satisfaction because everyone wants to work on nice and clean software and doesn't want to run after bug after bug after bug. So overall, there's a lot of productivity increases, and those customers that measured it in the past come to a net increase in productivity by 10 to 15%. Net productivity increase means they already deducted work to establish coding rules, work to document architectures. So it's really, really worth it to have a look on how static code analysis and architecture verification can help you and your projects. So thank you very much. And if you agree that this is a great thing, please reach out, and we're happy to make it possible with your projects as well. Thank you very much.